Praneeth is a colleague, good friend, researcher at Microsoft Research in Bangalore, and in my opinion, one of the best researchers in the area of optimization these days. You might have seen some of his papers in the conferences that we care about. There was an oral presentation last year at ICLR, right? And some fun facts about Praneeth, other than the fact that he's a great researcher. He was my lab mate at UT Austin when we were doing our PhD. He was also my neighbor, and for some time we shared the same Wi-Fi connection. Okay, and he has also seen me when I had long hair, so he knows how that disaster looks like. so with that picture, I will leave you with Praneeth. Thank you.
Thanks, Yanis, for the introduction, and thank you all for coming. So the title of the talk is on momentum methods and acceleration and stochastic optimization. And this is joint work with my colleague Prateek Jain from Microsoft Research in India, Sham Kakade and Rahul Kedambari from the University of Washington, and Aaron Trickford from Stanford. Before I get into the details of the talk, let me give you a high-level overview of the kind of work that we have been doing. And as most of us are probably already aware of, optimization is a crucial part of large-scale machine learning these days. And stochastic optimization-based methods, such as stochastic gradient descent, are the workhorses that power these optimization algorithms, right? And there are several aspects of stochastic gradient descent that people use in practice. So examples include mini batching, where we compute the stochastic gradient not on single examples, but on a collection of mini batch of examples. Then the second one that I mentioned here is model averaging, where especially in the context of distributed optimization, where we have multiple machines and we train maybe different models on different machines. And then we want to combine all of these different models to get a much better model than each of them individually is. Then the third one is acceleration, which is an optimization technique which has been developed to speed up the convergence of gradient-based algorithms so that they run faster. And this is also used in practice. And finally, the one that I mentioned here is about learning rate schedules. So what is the initial learning rate that I should choose? And as the algorithm progresses, how should I change the learning rate to get the best performance out of the algorithm, right? So these are some of the key aspects of stochastic gradient descent. And empirically, people do a lot of work on figuring out how to choose each of these things in order to get the best performance out of the implementation, right? While these are very important in practice, from a theoretical point of view, there is very little understanding of how exactly all these things affect the performance of stochastic gradient descent, even on simple problems. So our work focuses on a thorough investigation of all of these aspects for the specific case of stochastic linear regression. Okay, and the reason we work with stochastic linear regression is because the simple structure of the problem. I'll explain what exactly is stochastic linear regression. Okay, but the reason we work on like this very specific and simple problem is that already in this context, answering all of these questions already becomes non-trivial. But it is possible to do it, and the very simple structure of the problem helps us actually answer these questions. And the second thing is, even though whatever we do from a theoretical point of view applies only to stochastic linear regression, the high-level conclusions that we draw from this analysis seem to carry over to more complicated models as well. So that's the background, and in this talk I'll be exclusively focusing on the work that we did on acceleration in the stochastic setting for the stochastic linear regression. Okay. So let me now start by giving you a brief primer on optimization, and there is no better place to start than gradient descent, which is one of the most fundamental optimization algorithms. So given a function f that we wish to minimize, gradient descent computes the gradient at the current point and then moves in the negative direction of the gradient, right? So there is a parameter step size, and then we move in the negative gradient direction depending on how large the step size is. And as I mentioned, we will be solely interested in this talk for about the linear regression problem, where the function f that we wish to minimize is given by x transpose w minus y square. Here x is a matrix. W is a vector and Y is a vector. So X and Y are given to us, and we wish to minimize this function over W. So that's the problem. And as you can imagine, this is an extremely basic problem and arises in several applications. And because of this reason, this has been extensively studied in literature. Okay. And one of the most basic questions that arises here is, if we use gradient descent for solving this linear regression problem, how fast do we expect gradient descent to actually find a solution to this problem, right? And in order to quantify this notion, I need to define this quantity called the condition number of the problem. So the condition number is given by the ratio of the largest eigenvalue of this matrix XX transpose to the smallest eigenvalue of XX. Okay. Yeah.
The smallest eigenvalue is 0.
Yeah. So then, okay. So there are two kind of analysis that you can do. One is you get this geometric convergence rate, so you get a log dependence on this one. So you can also do a analysis where this is equal to 0. You get a different kind of convergence rate. So in this talk, I'll be focusing on the what is known as a strongly convex setting, where this is not equal to 0. And the result you get usually for strongly convex can also be transferred to the non-strongly convex by adding a regularizer and instantiating this. So we assume that the setting is that the condition number is not infinity, meaning that like the minimum eigenvalue is not equal to 0. Okay. In this context, if I denote by f star the minimum value of f, and epsilon is my target of optimality, meaning that I want to find a point w such that f of w minus f star is at most epsilon. Okay, this is my target. Then the number of iterations that gradient descent takes, find such a point which satisfies this inequality, is known to be condition number kappa, which is defined here, right? Condition number times log of initials of optimality divided by target of. So this is the number of iterations that gradient descent requires. Find an epsilon target of suboptimal. Okay, and the larger kappa is, the number of iterations required is larger. Okay. Okay. So the natural question here is whether this rate that we have here is this tight. So so for gradient descent, when I put this theta here, it means that for gradient descent, this is not to be tight, meaning that there are problems where gradient descent does require these many number of iterations to actually find an epsilon suboptimal solution. So the question is, can we design a new algorithm which can do better than this condition number, linear dependence on the condition number? So the thing in the log is usually not of too much importance. So what we are mostly interested in is this dependence on condition number, which is linear here. Okay, and a natural question is whether we can improve the dependence on condition number from linear to something better. Okay, and the hope is that gradient descent does not actually reuse any of the past gradients. At any iteration, I'm using only the current gradient. I don't, even though I have seen grad f of w t minus 1, t minus 2, and so on, I'm only using the current gradient. So can we design a more intelligent algorithm which uses maybe all the past gradients as well, that can actually get me a better convergence rate? And it turns out this intuition is correct, and there have been several famous algorithms which do this. Examples include conjugate gradient, Polyak's heavy ball method, and Nesterov's accelerated gradient method. Okay. These methods in general are also known as momentum methods. And as a representative example, let us look at Nesterov's accelerated gradient descent, how it looks like, and what is its convergence rate. So the Nesterov's accelerated gradient descent maintains two iterates, Vt and Wt. So gradient descent only had one iterate, whereas Nesterov's accelerated gradient has two iterates, Vt and Wt. And there are two kinds of steps. So one kind of steps are the gradient steps, the other ones are momentum steps. So from Vt, we take a gradient step to get Wt plus 1, and from Wt plus 1, we take a momentum step to get Vt plus 1. And then from Vt plus 1, we again take a gradient step to get Wt plus 2 and so on. So we have two iterates and two kinds of steps, and this is how the algorithm proceeds. Okay. In equation form, this is how it looks like. And the exact form of the equations is not important, but what I want to stress here is that the amount of time taken per update of per iteration of Nesterov's accelerated gradient is pretty much the same as that taken by an iteration of gradient descent. Okay. So in terms of per iteration cost, the amount of time taken to implement one iteration of Nesterov's accelerated gradient is pretty much the same as the amount of time taken for one iteration of gradient descent. However, the convergence rate, meaning the number of iterations required, turn out to be square root of condition number rather than a linear dependence on condition number that we had for gradient descent. Okay, so for gradient descent we had this linear dependence on condition number, whereas for accelerated gradient descent we have the square root of condition number. And condition number is a quantity which is always greater than equal to 1 because it's max over min, so it's always greater than equal to 1. Square root kappa is always better than kappa. Okay, so the accelerated gradient method is always better than gradient descent. And one might wonder whether this theta actually hides like very large constant factors and whether this is really practically useful or not. And it turns out that, like, even on simple examples, this is already extremely much better than gradient descent. So here I am showing you plots for gradient descent in the blue and accelerated gradient in the red for a 100-dimensional linear regression problem with condition number about 100. And you can already see that the error on the y-axis, so accelerated gradient is about 10 times faster than gradient descent to reach the same level of accuracy. Okay, so even in practice, this is like extremely useful and gives a lot of improvements over gradients. So this was all the background that I wanted to give you on optimization in the deterministic settings. Now let's look at the kind of optimization problems we encounter in machine learning. So in machine learning, we usually don't have a fixed function. So we get, I'm thinking of, like, say, the supervised setting where we get n samples from an underlying distribution, x1, y1 all the way up to xn, yn. Okay, and we usually write down the empirical function, which is 1 over n, number of samples, summation over I over all the samples. In the linear regression setting, xi transpose w minus yi whole square. Right? We are trying to fit a linear predictor to xi comma yi, and in practice, what we do is solve this empirical problem, which is 1 over n summation I xi transpose w minus yi whole square. Okay, but the ultimate goal of our ultimate objective is actually not to get very good accuracy on this empirical problem, but rather to get a very good error on the true expectation over the true distribution. Right. So my ultimate goal is to actually minimize expectation over the distribution of x transpose w minus y whole square. Right. This is my ultimate goal. And you cannot directly apply gradient descent on this problem, right? That's because gradients here involve computing an expectation over the underlying distribution, and we don't have access to the exact distribution. All we have access to is samples that we have seen from the distribution. So this setting has been extremely well studied and goes by the name of stochastic approximation. And there is a natural way to extend gradient descent to the stochastic approximation setting. And that's the motivation for the original paper that actually proposed the stochastic gradient descent algorithm. Okay, what is the main idea? So the idea is that you take gradient descent, but then replace the gradient with a stochastic gradient, where the stochastic gradient has been computed just using one particular data point xt comma y. Okay, and in expectation, the stochastic gradient is equal to the gradient because this xt yt comes from the same underlying distribution that you are trying to optimize over. And for linear regression, the update takes this very simple form. So the next iterate wt plus 1 is wt minus delta times this is the stochastic gradient. And it's extremely easy to compute the stochastic gradient because you just compute this inner product and then you do this linear update. And because of its extremely efficient nature, it's very widely used in practice. And that's also the reason for its usage in deep learning and many of the large-scale machine learning problems where computation is extremely important. Okay, and I told you how to convert gradient descent to stochastic gradient descent. In practice, people also use variations of other algorithms. So I spoke about heavy ball method. So if you replace gradients with stochastic gradients in heavy ball method, you get a stochastic heavy ball. And similarly, if you do it for Nesterov, you get a stochastic Nesterov accelerated. Okay, so these are straightforward extensions of deterministic algorithms to the stochastic setting, and these are actually algorithms that people use in practice. Now, let us try to understand what is the convergence rate of stochastic gradient descent in the stochastic optimization setting, right? So, just like we had in the deterministic setting, the convergence rate here. Okay, so let me first consider the special case where there is a true W star and my actual Y. So the Y that I observe is actually equal to X transpose W star. So there is an underlying truth, and let me tell you what the convergence rate in this low noise model where there is an underlying true W star. Okay. In this rate, we can again get a similar convergence rate as what we got in the deterministic setting. So you have linear dependence on condition number kappa, log of initial over target for optimality. There is a slight difference in the way you define the condition number because you are in the stochastic setting, but the convergence rate per se remains the same. And in the noisy case where you have an additive noise term, so y is actually equal to x transpose w star plus an additive noise, you have an additive term in the convergence rate which depends on the noise variance sigma square. Okay? Yeah.
Why is there a tilde on the theta? What's hidden in the tilde?
Log factors on log kappa.
Okay. Is this what's called the realizable case?
So this is a realizable case. No noise case is a realizable case.
All right.
Yeah.
So you have linear convergence rate because all the gradients,
gradients all decrease as you get closer.
Goes
Yeah.
to zero. So
You don't need variance reduction. Right. So, and in this case, you will get an additive term based on noise variance. Yeah.
and this time you
You'll not. Yeah, you'll need variance reduction to get them. Yeah.
Range of values.
I mean, it depends on your problem. It could be anything greater than or equal to 1. Yeah. Greater than or equal to 1. Okay, so now let me try to recap all the things that we have seen so far. So in the deterministic case, we saw that gradient descent has a linear convergence, a linear dependence on the condition number, and Nesterov accelerated gradient has a square root dependence on this condition number. Right? This improves, and it turns out like this is the optimal for the deterministic setting as well. Okay. Okay. So now in the stochastic setting, we have this linear dependence on condition number, and then of course an additive term that depends on the noise variance. Okay. So the question we want to ask is: acceleration in the stochastic setting possible, just like what we did in the deterministic setting? So in the deterministic setting, we improve kappa to a square root of kappa. In the stochastic setting, can we do something better than stochastic gradient? Okay, so that's the broad question that we want to ask. And I need to qualify this a bit more because it turns out that at least the second term is statistically optimal. Okay, there is no algorithm that can actually improve upon this second term. So all you can improve on is actually only this first term. So that's basically the question that we ask, and more precisely, can we improve this dependence on the condition number kappa here? So that's the question that we are asking. Okay, is the question clear? Yeah.
Just I'm used to seeing I think 1 over square root epsilon. And for the variance stuff, right? So can you explain a bit why we would be 1 over epsilon?
So for okay, so if you so because you're already looking at this square loss kind of thing, right? So the law, so if you're looking at stochastic linear regression, you have a x minus x, w minus w star square, right? And w minus w star, that would depend on the order of 1 over square root n. And because you are looking at the function value difference, which is a square, you will get, and w star you are able to estimate within 1 over square root n. And because you are looking at the square error, you will get a 1 over n here. That's the reason.
So this is only for linear regression?
This is for linear regression, yeah. And any kind of smooth problems, you will see this kind of rate. Because like here the optimum grade will be equal to 0. And then like the error is only in the quadratic term. That's why we are.
What is the lower bound known for like general gradient based methods for like for stochastic optimization? I'm gonna correct that. like for the bad setting, like Nesterov proved some lower bounds.
Yeah.
What's the lower bound?
Yeah. So in this setting, so if you look at the stochastic approximation setting, there are no computational lower bounds. There are only statistical lower bounds.
Okay.
And those statistical lower bounds only capture this term.
Okay.
They don't capture this term.
That's
for
for
the
the
ERM setting.
Sorry, that was for the online stochastic setting, right? It's the online and the offline setting.
This is like just statistical bound. It doesn't matter what algorithm you use. You cannot improve upon this.
I think if you have an offline method, I mean, we can take this offline, but the informational theoretic bounds hold for the online setting. Maybe
information theoretic bounds hold for both online and offline. They don't care about how you do the computation.
Okay.
It's just like if you see these many samples, this is the best you can.
For the true expectation, Like if you, yeah, okay, so, because like if you just want to minimize the finite sum formulation.
Yeah, if you want to do the finite sum, then you have computational lower bounds. But if you care about the true expectation, the information theoretic lower bound say if you see these many samples, this is the best you can.
So why there is in the previous slide there is no term that depends on the variance because it's coming from the discrepancy.
Yeah, so I said like in the previous thing, I assume there's no noise setting, and that's where I get this. In the noisy case, you do have this additive term, and that's basically what I have.
Okay, so this is
Yeah, this is the. Yeah.
So here you're making the distinction recognizing the empirical loss
Yeah.
and the actual expected loss. That's the question.
Yeah.
If it was the empirical loss, you can accelerate.
Yeah, that's right. That's right. That's right.
Very different question.
Okay. Okay. So before I try to answer this question, so let me first tell you why we think this is really important. And the reason is that as we saw earlier, right? So heavy ball and Nestorov's accelerated gradient, which were proposed for the deterministic setting, you can easily make them stochastic by just replacing gradients with stochastic gradients, and people do use them in practice a lot. And any deep learning like package that you look at has these additional momentum parameters. We basically implement these other algorithms, and people do use them in practice. And so in the deterministic setting, we already saw like acceleration can actually give like orders of magnitude of improvement. And even in these stochastic settings, it seems like people are actually observing a lot of improvements. And there is some of our earlier work as well, which shows that if you can accelerate, it could help you in designing more parallel algorithms as well. So on the whole, the point I'm trying to make here is that in practice, we do expect to get good improvement if we can accelerate in the stochastic setting. But and right now people are using heuristics, and we would like to understand whether there is a sound way to actually be able to do this even in the stochastic setting. Okay, and there has been some earlier work on understanding stochastic heavy ball and Nesterov in the in some optimization settings by Bias-Variance and Delimi and Lan. But the setting that they consider is different from the machine learning setting, and so in short, they consider like fixed variance settings, which are not reflective of like the stochastic linear regression problem and so on. But if you are more interested in the difference in settings, I can talk to you more in detail offline. Okay. Okay. So with this, let me try to give you a broad outline of our results, and then I'll go into each of the. So the first question that we ask is whether it's possible to improve the linear to a square root, just like we had in the deterministic setting. And it turns out the answer to this is no. And there are cases where, like information theoretically, it's not possible to improve the condition number dependence. So is it ever possible to improve? And actually can be improved on some problems, but then it has to depend on other problem parameters and not just on the condition number. Okay. And the third thing is, because we are saying that in some cases improvement is possible to existing algorithms like the stochastic versions of heavy ball Nesterov that people are using in practice, do they achieve this improvement whenever it is possible? And the surprising answer to this turns out to be that they cannot, and in fact they are no better than SGD. And this is actually very surprising, also given the fact that in practice, like people are using this and they are observing some speedups. So I'll get to this like apparent contradiction towards the end of my talk. Okay. And the final question that we ask is whether we can, so because these methods don't work, can we design a new algorithm which actually improves our stochastic gradient design and get some provable improvements on this problem? And we do design such an algorithm, which we call accelerated stochastic gradient descent, or ASGD. Okay. So are the results clear? I'll explain each of them in more detail next. So the first question is whether it's always possible to accelerate stochastic gradient descent. And I'll try to illustrate the answer to this question by using an example. And again, like let's just consider a noiseless setting where there is a true W star and y is equal to x transpose W star. Yeah.
When you said that in practice people observed an acceleration, was it like for like deep learning?
Yeah, for deep learning.
Convex objective.
Yeah.
So it might be related to the non-convexity.
It could be related to non-convexity. Yeah.
That's just.
It's possible, but I'll get to it towards the end of my talk. Yeah. So so the first question that we ask is whether acceleration is always possible, and we'll try to answer this question in the context of like realizable model where y is actually equal to x transpose w star for some fixed w star, right? Okay. So in this setting, the convergence rate of SGD is given by, as we saw earlier, condition number log of quantity, and one would hope that maybe we can improve this condition number to a square root of condition number, right? So that's the hope going from the deterministic state. So more concretely, so let me define a distribution over X, which is two-dimensional vector. So it's equal to 1, 0 with probability 0.9999 and 0, 1 with probability 0.0001. Okay. So most of the times it's 1, 0, and very, very few times it's 0, 1. And in this case, the condition number turns out to be 1 over this probability, which is 10 to the 4th. Okay. And the question we are asking is whether we can get a convergence rate of square root of condition number log of this quantity. And a simpler question, if you want to just ignore this log, is to say, if I'm given an initial point, can I halve the error of the initial point using square root of condition number or about 100 samples? Okay. So if I just give you 100 steps or 100 samples, can you halve the initial error? And once you stare at it for some time, it's actually not difficult to see that if you have any fewer than 10 to the 4 samples, right, you are never going to observe an example in this direction, right? Because this probability is like 10 to the minus 4. So if you observe any fewer than 10 to the 4 samples, you are not going to observe x equal to 0, 1, right? Which means that in W star, the vector that you're trying to estimate, you have no measurement on the second coordinate, because only if you get x equal to 0, 1 can you actually measure something about the second coordinate. And if you never see the 0, 1 direction, then you cannot measure the second coordinate. So in fewer than 10 to the 4 samples, you cannot estimate the second component of W star at all, right? So what this basically says is that we cannot hope to do anything better than condition number, like in an information theoretic sense. It's not about competition or anything. Just information theoretically, you cannot do anything better than condition number. So acceleration is not possible at all for this distribution. Okay. So this answers the first question in negative, that we cannot always improve this condition number to square root condition. Yeah.
Okay, so you have that table earlier, and it said you had 3 of the blocks, and you were missing the top right, the bottom right block, right? And on one of them, you had the accelerated number of iterations. There was a root kappa, right? In the first term, and there was a second term that was due to noise variance, right? So you had 2 terms.
Yeah, SGD has condition number on the first term and noise variance on the second.
Exactly. Yeah. So my question is, any chance like something similar is happening in this case? Like, could you actually say that what you're getting here is something that is a multi-term result, and the first term is actually root kappa, but it's hidden by bigger terms? You see what I'm talking about?
No. So okay. So in the deterministic setting, there is only one term, right? In the deterministic setting, there is only one term. Only in the stochastic setting, there are 2 terms.
Exactly.
And there may be some lower order square root kappa terms possible, but the point is the dominating term is this kappa, and the question is, can you decrease the dominating term? Is the question. Like, if you cannot decrease the dominating term, the presence of other terms is.
All I'm saying is that you designed this example in a way that maybe we can come up with a similar example in the SGD case, right? Similarly, that tells us no, we cannot have this acceleration, because we have this extra noise, right? So what you're doing here is, in some sense, you're hiding.
Yeah, there is a sampling kind of noise.
Yes,
and that's what makes it impossible to do it in the stochastic.
Right.
And that's what I'm saying. That's all I'm saying. Yeah.
Okay.
Yeah. So I'm saying that it's not always possible. Okay?
Right.
That's what I'm saying.
Right.
Okay. So now let's get to our second example. So instead of considering a discrete distribution, let's consider a Gaussian distribution, which again has the same covariance matrix. So X is normal 0, h, where h is the covariance matrix with 0.9999 and 0.0001 on the diagonals. So in this case, the condition number is again like 10 to the 4, which is same as the previous setting, right? The condition number is still again pretty large. But it turns out that after just 2 samples, right? You get just 2 samples. The 2 samples that you get are linearly independent because you are drawing from a Gaussian distribution. And if you get two independent samples, you can actually invert the empirical covariance matrix, and then you can exactly find W star, because like we were looking at the noiseless problem, and you can exactly find W star. So in this setting, at least information theoretically, it seems like after two samples, you have enough information to find W star. Whereas in the previous setting, you did not have enough information after at least 10 to the 4 samples were required, right? So in this setting, at least information theoretically, it suggests that acceleration might be possible. And the key takeaway here is again that it depends on some other problem structure and not just the condition number. Because we saw two problems with the same condition number, one where acceleration was not possible and the other one where acceleration seems possible. So what exactly is the problem parameter that seems to capture this? And that becomes clear when you look at what we are doing here, which is that we are inverting the empirical covariance matrix. So the key property that we want from the samples that we have gotten is that we should be able to say that the empirical covariance matrix, which is 1 over m summation xi transpose, this is the empirical covariance matrix, it has to be close to the true covariance matrix H. If it is close, then information theoretically at least we have enough information to be able to recover W star, and if it is not close, then we don't have enough information theoretically. So how many samples do we really require for the empirical covariance matrix and the true covariance matrix to be true? This is a very well studied question in random matrix theory, and just like we have a notion of variance for scalars, we have a notion for variance notion for matrices, which is called matrix variance. And in the context of the current problem, we call it statistical condition number and denote it with kappa twiddle. Okay. Okay. So we define this new notion called statistical condition number, which we denoted by kappa twiddle. So what exactly is this kappa twiddle? For that, let's first look at the Hessian H. Okay. So or the covariance matrix H. So H is the covariance matrix of the distribution that I'm looking at. Okay. And these E's correspond to the eigendirections of H. Okay. So this H corresponds to the ellipse corresponding. So any matrix any positive semi-definite matrix corresponds to an ellipse. So I'm just drawing that ellipse here, and the principal axis of this ellipse correspond to the eigendirections of H. Okay. And the statistical condition number kappa twiddle is essentially the sum over all of these eigendirections of E transpose xi square divided by the expected value of E transpose xi square. Okay. On the other hand, the computational condition number that we have defined is norm of xi square divided by min over the eigendirections of expected value of E transpose xi square. Now, if you take the summation over all E, this is nothing but norm of xi square, and then you are replacing the sum in the denominator with the minimum. So it follows that the statistical condition number is always less than or equal to the computational condition number, and acceleration might be possible if this kappa twiddle is much smaller than kappa. Okay, because kappa twiddle we are saying is kind of information theoretically necessary for us, and if the information theoretic lower bound is much smaller than the condition number, then we can hope for acceleration to happen. Okay,
I think you're doing it. Well, there's some switches.
I see. Okay.
It's happened to me a lot.
Okay. So, what are the values of the statistical condition number and computational condition number in the discrete and Gaussian settings that we saw so far? So, in the discrete setting, both of them turn out to be of the same order. So, we do not expect any acceleration to happen. And in the Gaussian setting, the statistical condition number turns out to be about 100, whereas the computational condition number turns out to be of the order of 10 to the 4. Okay. And let me try to illustrate like all the things that I said in these two pictures. So the picture to the left is a plot of the discrete distribution. This one is on the Gaussian distribution. Okay, and the y-axis is the error, and x-axis is number of iterations or number of samples. The green plot corresponds to the performance of stochastic gradient descent on the discrete thing and on the Gaussian, and the pink dotted line corresponds to the statistical condition number of both these settings. So here it's about 10 to the 4th, and here it's about 100. Okay. Okay. So now look at when stochastic gradient descent starts to perform very well on each of these problems. So the error starts to decrease rapidly after this 10 to the 4 or 10 to the 5 iterations, which is very close to the condition number. And even here, it happens at a very similar pace, about 10 to the 5. Okay. Whereas, so this really is the behavior of the algorithm. I'm not giving you an upper bound and talking about upper bound, but rather this is the true behavior of the algorithm. And the pink dotted line, which is the lower bound, so there is very little gap between the lower bound and the performance of SGD here, whereas there is a big gap between the lower bound and the performance of SGD in this context. So this again reinforces the conjecture that in the discrete setting, at least we know that acceleration is not possible because there is no gap between like the performance of SGD and the lower bound. Whereas in the Gaussian setting, there is a significant gap between the lower bound and the performance of SGD, so there is scope for acceleration in this setting. Yeah.
Like for your definition of the kappa tilde,
Yeah.
you don't get, is it a summation of all the possible vectors?
All eigenvectors.
Or just the eigenvectors?
Just eigenvectors.
Okay.
Yeah.
And like you don't have to need to normalize by the number, the dimension or something?
So even in the denominator, so no, you don't, because usually, okay, so like in most, not like if your samples are only one vector at a time, this is at least equal to the dimension. Because if you don't even see dimension number of vectors, your matrix is not even full rank. Your empirical covariance matrix is not even full rank. So this is usually at least the dimension for strongly convex problems.
So is the eigenvector of H?
Yes.
So like the denominator is equal to the eigenvalues, right?
Yeah, these are the eigenvalues. Yeah, and as you can see here, the min, this is the smallest eigenvalue. So, yeah. Correct. Okay. Okay. So what I have told you so far is that there are cases where acceleration is not possible in the stochastic setting, and there are cases when it seems possible. And the next question is whether existing stochastic versions of like heavy ball and Nesterov achieve improvement whenever there is this gap in settings where there is this gap between the lower bound and upper bound, okay, where kappa twiddle is much smaller than kappa. And the surprising answer to this turns out to be no, and we consider distributions where kappa twiddle is actually much smaller than kappa, but the rate of stochastic heavy ball is no better than that of stochastic gradient descent. So by omega, I mean that it actually behaves like this. It does not, it's not faster than, so the number of iterations required for heavy ball is at least linear in condition number. Okay. Okay. So this basically says that stochastic heavy ball is no better than SGD, and while we can like thoroughly and rigorously show this for heavy ball, the same statement seems to be true empirically for Nesterov accelerated gradient as well. And I should also point out that the distributions that we construct here are actually fairly natural distributions. And in fact, if you look at the Gaussian example that we saw earlier, so I'm in addition to SGD, I'm also plotting heavy ball and Nesterov, which seem to be like pretty much on top of each other. So, and they don't really do any better than stochastic gradient descent. Okay. So the answer to this third question is that the existing algorithms, heavy ball and Nesterov accelerated gradient, not really achieve improvement in the stochastic setting, even where it might be possible. Yeah.
Go back to the previous slide. But if you were just sampling an empirical distribution using stochastic gradients, you would see the acceleration. At some point, is that true? And what's happening is you're just missing the true. That's true.
No, I did not get your question. But if
I'm saying, so here you're resampling from the.
Yeah, I mean here we think that like this is a Gaussian, right? So we are getting fresh samples every time from the same underlying Gaussian.
But
yeah.
If you would say just take them.
Yeah.
Use that empirically.
Yeah.
I'm curious what the curve would look like.
So even then you will have this issue because then your distribution is not the Gaussian, but then the discrete point sets. But even there, you don't really observe acceleration due to heavy ball and stuff. So even in those settings,
get acceleration empirical.
No, you don't get unless you are using like full batch gradient descent. So let me come back towards the end of this talk. I'll explicitly point out why wherever heavy ball and Nesterov get improvement, I'll explicitly point out where you think. Yeah.
Yeah, we'll get to that later, but I also think there exist cases where you can see.
Oh yeah, there definitely exist cases.
Acceleration down to the noise floor in some sense.
Yeah. So I'm not okay. So let me put this in context. So I'm not saying that they never get acceleration. That's not the point that I'm trying to make. I'm saying that as a general principle, don't get it. Maybe there are like very special problems where they do get it, but I'm saying in terms of like
in terms of a worst case.
In
You're
terms
saying
of
there
worst
exist cases where you don't.
yeah,
get it.
and I'm saying they're not like some like pathological cases that I cooked up, but rather like fairly natural distributions like Gaussian distributions where it does not. What I'm saying. Okay. So this brings us to the final question, which is whether we can actually design an algorithm which probably improves upon the performance of SGD in all the situations where there is a big gap between kappa twiddle and kappa, and we do indeed design such an algorithm which we call accelerated stochastic gradient descent, or ASGD for short, which improves the condition number kappa dependence in SGD to a square root of kappa twiddle. Okay, so because kappa twiddle, as we saw, is always less than or equal to kappa, there is always an improvement over kappa, right? And whenever kappa twiddle is much smaller than kappa, this is a significant improvement over kappa. Okay, so this is the main result for the algorithm that we have. Okay, so this is again like an empirical demonstration of our algorithm in the red. So in this case, the statistical condition number is about 100. So we expect a speed up of about 10 because we have the square root of kappa twiddle, right? And that's basically what we observe between both like the green gradient descent and the red ASGD, as well as like heavy ball Nesterov and ASGD as well. Okay. And one more thing is that there is still a large gap between the lower bound pink line that we have here and the performance of our algorithm. And we do believe that this is probably unimprovable because of computational reasons, but there have not yet been any lower bounds, computational lower bounds on the performance of stochastic algorithms. So it will be an interesting direction for future work to like either improve the algorithm or show that it's not possible. Okay. So what is the algorithm that we use? So the algorithm that we use, it's hard to give a very good intuition, but let me try a high-level picture. So the way that people convert deterministic to stochastic algorithms, so for Nesterov accelerated gradient in particular, is that there is a 2-iterate version, which I told you about in the beginning, which has this interpretation of having gradient steps and momentum steps, and that's the one that's widely used in practice. Whereas there are also other ways to write Nesterov's accelerated gradient descent in the deterministic setting, and one of them is this 4-iterate version, which has this interpretation of upper and lower bounds. So you have a primal, and then you have a dual, and then you are trying to minimize the difference between the upper bound and the lower bound. And you can also think of Nesterov's accelerated gradient descent trying to do this. And there is a different 4-iterate version. And in the deterministic setting, both of these algorithms are exactly the same. Whereas if you replace gradients with stochastic gradients, right, the algorithms become actually completely different. They're no longer the same. So the algorithm that we propose is essentially this 4-iterate version with using stochastic gradients rather than gradients here. Okay, so the algorithm is same as Nesterov's accelerated gradient or a version of Nesterov's accelerated gradient, but it is important the way you replace gradients with stochastic gradients. Not all of them will give you the same algorithm, and doing it more carefully turns out to be the right way to actually do it. Okay. I'll maybe spend like a few minutes on the high-level overview of the proof. So as we saw, like there are two components to the guarantee. So there is this first term which depends on the condition number, and then logarithm, and then the second term which depends on the noise variance, right? So there is by standard analysis of the stochastic based methods, it turns out there is what is known as bias-variance decomposition, and this first term is known as the bias, and the second term is known as the variance. And there is a nice way to decouple them so you can analyze them independently, like separately. And that's what we do. So for the first term, the main intuition is that if you look at the potential function that is used in the proof of the deterministic version of Nesterov's accelerated gradient, it has two iterates, right, Wt and Vt, and then the potential function that one uses measures the error in Wt and Vt in different norms. So you measure the error in Wt in the H norm, H is the covariance matrix, and in the Vt in the L2 norm. So the main intuition that we had here was that we can actually replace this h and 2 norm by any powers of h to the a and h to the a minus 1, and the same analysis goes through. And in the stochastic setting, it turns out that using the L2 norm here and then the h inverse norm here is the right thing to do, and that's what gives you the right dependence on statistical condition. And once you do this, you get standard analysis that potential function at t is less than or equal to 1 minus 1 over square root kappa kappa twiddle and potential function at t minus 1, and this gives you this geometric decay. And the square root of kappa kappa twiddle that you see here is basically what gives you corresponding term, the convergence rate. Okay. Yeah.
So you said they're not equivalent, right?
Yeah.
Why did you say the same one is using the norm 2 for the first term and norm h minus 1?
Oh, okay. So there are different analysis also. So this 2-iterate version has a different analysis based on like gradient momentum interpretation, and this 4-iterate like upper and lower bound interpretation is basically what gives you this kind of potential function analysis.
Why is the second you said it's better or the thing to be done?
So I don't know if I have very good intuition. So somehow like this upper and lower bound interpretation carries over better to the stochastic setting, but the gradient and momentum interpretation is not clear. Even the proof, not clear at all how it would go into the stochastic setting. But when you look at the upper and lower bound interpretation and you have gradients being replaced with stochastic gradients, clear that you have to bound the variance in a certain way and then things work out. Yeah, so in some sense, like I don't have like too much more intuition than what the proof tells me. Okay, so this was about like the first term in the convergence part, and then there is the second term which turns out to be like much more challenging. And the main reason for the challenge is that any kind of potential function argument where you keep track of a single scalar quantity and understand how it decays every step does not seem to work and seems to be extremely loose. So we have to essentially keep track of like the entire covariance matrix. So if WT and UT are the iterates, then theta T is the covariance matrix of these iterates at the kth step, and theta T plus 1, theta T satisfies this nice linear recurrence property. And when you expand theta to at the pretty much like after a large number of steps, you get this nice closed form expression I minus B inverse, where B is an operator that acts on PSD matrices. Okay. So we essentially need to understand this I minus B inverse noise transpose. Fortunately, like B has eigenvalues less than 1, so this actually is meaningful. But then we actually have singular values greater than 1, which means that we cannot directly use some crude upper bounds operator norm of B to actually do the analysis. And the way we overcome this is to actually solve one-dimensional versions of this problem. So you have like small 4x4 kind of problems. Then you solve this in each dimension, and then you use condition number bound and statistical condition number bound to combine the various dimensions that you have solved into a single thing. So while all of this is pretty technical and like quite involved, there is one nice kind of statement that we can say, which is that if you look at T and you look at its covariance matrix, it's less than or equal to statistical condition number times H inverse plus delta times identity. So this gives you a way of bounding the covariance of the iterates around W star. Okay. So let me try to recap whatever we have seen so far. So for linear regression, we have pretty much completely theoretically understood the behavior of various algorithms: stochastic gradient descent, heavy ball, Nesterov, and then new accelerated gradient descent. And we showed that heavy ball and Nesterov don't really provide any improvement in the worst case setting, whereas ASGD does provide improvement over all of these other algorithms. Okay. Now the question is, like, we have thoroughly understood these questions for the linear regression problem. Does any of do any of these conclusions have any relevance to more complicated problems, in particular, say, training neural networks? Do any of these intuitions actually help us in understanding these things better, right? And the first question, when you come to this practice question, so the first question that pops in our mind is, in practice, people have indeed observed that stochastic heavy ball and Nesterov work much better than stochastic gradient descent in practice. So whereas we are saying that in linear regression, like you cannot really expect any improvement in the first case. So what is the main reason? And we believe that the main reason for this is mini batching. So if you think about it, so if you have a large enough mini batch size, you're pretty much close to doing exact gradient descent. Because if there is, depending on how much randomness there is in the data, you have a mini batch size of say 128 or 256, then that may already be enough to give you pretty accurate estimate of the gradients, right? And in the deterministic setting, we know that heavy ball and Nesterov do indeed give improvements. So if you have a large enough mini batch size, you do expect to get improvements from heavy ball and Nesterov. And what exactly is small or large mini batch for the stochastic setting to be close to the deterministic setting depends on varies from data set to data set. But on data sets that we use in practice, one would think that the mini batch size that we are using is reasonably large enough to reduce the variance in the stochastic gradients, and that's why these heavy ball and Nesterov methods actually give improvements in practice. Okay, and the value of our algorithm ASGD could be that it can improve upon the performance of SGD even for small mini batches, because we saw that in stochastic linear regression, even with a small mini batch size of 1, we could still expect some improvements over all these other algorithms. Yeah.
In your simple Gaussian example, where you did all the experiments to show the advantage of SGD, have you tried to increase the mini batch size?
We have tried. I don't have the pictures here, but like it's gradual. Like heavy ball and Nesterov gradually get more and more improvement if you use like larger and larger mini sizes.
So related to that, can you estimate your kappa tilde?
Yeah, so this estimation we don't really have.
But can you estimate the mini batch version of kappa tilde?
Yeah. So okay, so the way kappa and kappa tilde will change with the mini batch is that till some point they just decrease linearly, and after some point they saturate at some level. That's the behavior. So now let me show some empirical like experiments that we did, like evaluating the performance of ASGD as well as understanding whether like this conjecture about mini batching is reasonable or not. So the first experiment that we did was training a deep autoencoder for MNIST using a very small mini batch size of 1, and on this, so here we see plots for stochastic gradient descent, heavy ball, and Nesterov, and all of them are pretty much on top of each other, and we don't really see any improvement for these heavy ball and Nesterov methods over SGD when we use like this very small mini batch size of 1. Okay, and at the same time, if we use the accelerated algorithm ASGD, we do see some improvement in the performance of in the speed of convergence of ASGD compared to all of the other 3 methods. So this is for this very small mini batch size of 1. Okay. And we tried again training a ResNet on the CFA10 data set, again for a small mini batch size of 8. And so here are the plots for SGD, heavy ball, and Nesterov. And we again see that like there is not really much difference between the performance of these 3 methods. And if you look at Nesterov, which is as a representative example here, which like eventually achieves like the smallest error. So if you plot ASGD with respect to Nesterov, so ASGD does achieve the same asymptotic error, but decreases the initial error faster. And so even for this small batch size. Yeah?
Is it the training error or the test error?
This is a test error. And we did hyperparameter searches to get like the best test accuracy. So, and I mean, so hyperparameter searches are usually kind of tricky to get like totally correct. So we did our best to do it right. And so if you look at ASGD, it has like one more hyperparameter than Nesterov or heavy ball. But we made sure like that the number of total hyperparameter runs run for each algorithm is the same. Not like they are more because they have more hyperparameters. Okay. And finally, even for like the usual batch size that's used in practice, like 128 for training ResNet on again on CFAR 10. We see that like ASGD in the red, it achieves the same accuracy, but then decreases the initial error at a significantly faster rate. So if you are looking at exploratory search for hyperparameters, where we don't want to have all the hyperparameter runs run all the way through to the end, but rather run them till some point to figure out what are better ones to pick out and so on. In those cases, this like our algorithm could help speed up the hyperparameter runs. Okay? And so that's all I had to say. So let me just wrap up in this last slide. So in the deterministic setting, we saw that gradient descent has a linear dependence on the condition number, and accelerated gradient descent improves upon this dependence to get a square root. The stochastic approximation setting, SGD again has this linear dependence on the condition number, and the first question which is not clear is whether this can actually be improved to anything better, and it turns out that we cannot always do it, and there are some cases where we can do it, and the parameter that captures whether we can do it or not is this statistical condition number kappa twiddle, and we design an algorithm which actually improves this kappa to a square root of kappa twiddle, and we also show that stochastic versions of like popular momentum methods like heavy ball and Nesterov do not get kind of improvement. While all our theoretical results are for the stochastic linear regression problem, we have tried to evaluate it even on like more complicated models like training neural networks and so on. And the intuitions that we gain from the theoretical study seem to really carry over even to this more complicated settings. And finally, we also have code for our algorithm on PyTorch. So if you are training these models, please consider using our algorithm and let us know if you have any comments or observations. Okay, thank you.
There were a bunch of questions during, but now it's your time to ask more. Yes.
Yeah.
So I think I understand better what you're saying about if sigma squared is going to 0, then
yeah,
kappa tilde goes to 1.
So sigma squared and kappa twiddle actually are different. So in stochastic linear regression, right, there are two kinds of noise.
Okay.
One is I'm sampling an x,
yeah,
which rather than like giving you the entire distribution of x. The other one is if I give you an x, my observation y is equal to x transpose w star plus some additive noise.
right.
So there are two kinds of noise. One is additive, the other one is multiplicative. And the sigma squared captures the additive noise, and this kappa twiddle captures the what is called the multiplicative noise. So because I have this underlying Gaussian distribution, right? I don't see the entire distribution at once. I only see one sample. So that is what comes in this kappa twiddle. Even if I see that x, the observation I get is not exactly correct. So that, yeah.
What's the theoretical learning rate?
Sorry?
What is the learning rate given by the theory?
For
I don't know, for the accelerated.
Yeah, so it's not just one learning rate because the algorithm has like a bunch of parameters. So the learning rate, so there is one thing. So okay, so there are many ways again to look at it. You can look at it as a small learning rate, which corresponds to the usual learning rate, which is like 1 over smoothness, which is the same learning rate you would use in SGD, right? And then there is a long step. There is a large learning rate, which is more like 1 over. So the small step times 1 over. Small step times square root of kappa twiddle, and then there is one more parameter. So if you want more details, I'll be happy. Yeah.
In the stochastic setting, do you think it would be possible to end up with an algorithm that's the sort of convergence time is bounded only by kappa tilde?
No, I don't think so. That's what I was saying. That there are, so there is a big gap between like the lower bound that I showed you and then the performance. I believe it's not possible to improve upon this rate, but that'll be an interesting open question. Like either way, if you can design a better algorithm, you design a better algorithm or show a lower bound. But I tend to believe that a lower bound is
More questions? All right, let's thank Praneeth again.